A good way to think about absolute value is distance from 0 on the number line. The absolute value of 5 is equal to 5. The absolute value of negative 5 is also 5 because the distance from 0 to 5 is 5. The distance from 0 to negative 5 is also 5 on the number line. Now, a general definition goes like this. It looks a little confusing in one part, but it's the absolute value of any real number a is equal to a itself if a is positive or 0, but it's the negative of a, the opposite of a, if a is less than 0, if a is negative. And it's important to understand why this can designate the absolute value of a number, because we understand that absolute value refers to a number which is always positive. And it's commonly thought that this can't represent, or this doesn't represent a positive number, but certainly it does, because if a itself is negative, then the opposite of that negative number is a positive value. And we can even see it right here. The absolute value of negative 5 is 5. Well, let's use the definition to write the absolute value of this number. The absolute value of a negative number is the negative of that number. It's the negative of negative 5, you see, which is positive 5 as expected. So this represents a positive number. Now, some of the properties of absolute value you may recall are these, and I'm using here 5x. I'm using a number and a letter here. We could use a and b here for these factors and it would be just fine. I think you have that notation written in your textbook, but the absolute value of 5x can be written as the absolute value of 5 times the absolute value of x. That is, when you have the product within absolute value, that you can separate the two factors under the absolute value symbol, and you can go this way with that idea as well. So these are interchangeable. They're equal to one another. The absolute value of a quotient is the absolute value of the numerator over the absolute value of the denominator. The power idea, the absolute value of x to the fifth, can be calculated as the absolute value of x and then to the fifth power. Now, this is a rather interesting one. The square root of a squared is the absolute value of a. Now, you may think that, okay, square root and squaring, those are inverse operations. They kind of take one another out, and they kind of undo one another. So it should make some sense that we would get a here. But why absolute value? Well, it's the idea that if a itself is negative, then the square of a will be positive, and the square root of the positive number will be positive, but a itself was negative. So we can't say that the square root of a squared is always simply a, because a might be negative to begin with. Let me show an example. Suppose a is replaced with negative 5. You see, if we square negative 5, we get 25, but the square root of 25 is 5 and not the negative 5 that we started with. You see, but it is the absolute value of that negative 5 that we get as the answer. And this same kind of situation occurs whenever we have an even indexed radical and an even exponent that are the same. You see the index here and the number here. The fourth root of a to the fourth would be the absolute value of a. The sixth root of a to the sixth, and so on. There is a difference between distance and directed distance. When directed distance is used, when the word directed is part of that idea, then the distance has the distance notation, and the illustration of distance has a direction associated with it. So the direction could be positive or negative. But if we simply say the distance between a couple of things like cities, for example, we generally think about that value as a positive value, always, even though the direction may be opposite. That is, the distance from Orlando to Atlanta, you would say, is a positive value. The distance from Orlando to Miami, gee, that's an opposite direction from Atlanta, but we still say it's a positive number, you see, for the distance. So when we say just distance, we're talking about a positive number, but directed distance, we're talking about a distance or a value for the length of a segment, let's say, or the distance, but we also have a direction associated with it. And here, the directed distance from 4 to 10, you see a direction, the positive direction here, so it's going to be a positive number. And the way we calculate it is to take the destination and subtract the starting point. So it's 10 minus 4 or 6. But from 10 to 4, you see it's in the negative direction. It's to the left on the number line. And to make the calculation, you take the destination and subtract the starting point. So it's 4 minus 10, or negative 6. So the directed distance from 10 to 4 is negative 6. But the calculation is made, remember, as destination minus starting point. Now, the distance generally between a couple of points is a positive value, always positive, so absolute value comes into play. So we can say then the distance between 10 and 4 is the absolute value of 10 minus 4, or we could write it as the absolute value of 4 minus 10. Either way, we're going to get 6 for that distance between the 2 points. So distance and directed distance. Suppose we make the calculation of the directed distance from 4 to negative 3. Now remember, to make the calculation, you take destination and subtract starting point. You see negative 3 with negative 4, oh, that's negative 7. And does that make sense intuitively? Well, sure it does, because if we identify the position of 4 and the position of negative 3 on a number line, from 4 to negative 3, we're going in this direction, you see. Directed distance. So we have the 4 to 0, and then 3 more, that's negative 7 for that total. The distance generally between 4 and negative 3, though, is calculated as the absolute value of 4 minus negative 3. Now, it's just the difference between these two that are in the absolute value symbol. We can do it this way, or we can do it as negative 3 minus 4. You see, either way, start with either one. It's the relative difference of those two, though, within the absolute value symbol. This becomes 4 plus 3, or 7. Absolute value of 7 is 7. And here, as expected, negative 3 with negative 4, negative 7. Absolute value, again, 7. Here's a situation involving absolute value with inequality. Now, I want to show a couple of simple examples here, and then we're going to go to a more complicated form. But we can make an interpretation of the meaning of this by using a number line. Absolute value of x is less than 4. Well, absolute value means distance from 0 on the number line. So, gee, if we think about a number line and we think about the distance from 0 being less than 4, then that distance could be taken in either direction. So we're talking about all the numbers x that are in this interval, you see, from negative 4 to 4, that would make this true. So for all of these x values, the distance from 0 is less than 4. All right, so that's the idea. Now, we can form an inequality, compound inequality. We can form a couple of inequalities from this, actually. But we could say that, that x is between negative 4 and 4. We could say that this inequality, this absolute value inequality, implies that negative 4 is less than x and x is less than 4. X is between negative 4 and 4. All right, all interchangeable parts, sort of, in this idea. We could make two separate inequalities out of the situation, and I want to show that here as well, because some people might prefer this, might prefer saying that, well, let's see, we're talking about x values that are greater than negative 4, but also x values that are less than 4. Now, let me slide over just a little further. X is greater than negative 4, and x is less than 4. Now, the word "and" is in here because we're talking about x values that are in this interval and in that interval at the same time. It's important for us to know why that's the case. You see, if we're talking about x is greater than negative 4, if this is negative 4, and this is 4. All right, x is greater than negative 4. Gee, we're starting here and we're going out in this direction infinitely far. And x is less than 4, we're starting here and going in this direction infinitely far. So we want the overlap We want the values that are in this interval and in that interval at the same time. All right, so it's the intersection of these two sets that we're talking about here. Now, that's what happens if we separate. If we leave this as a compound inequality, it's pretty self-explanatory. All right, now think about this situation. And graphically, the distance from 0 on the number line is greater than 4. Here's 0. Should have put a 0 here. Anyway, the distance is greater than 4, so that distance could be out here, or the distance could be out here. But the distance is greater than 4 for all of these x values and for all of those x values. So the solution to this would be the numbers that fall in this interval and the numbers that fall in that interval all together in one big set. Well, how do we show that? Well, we can show it like this. We can say that this is the interval x is greater than 4. This is the interval x is less than negative 4. And we want values that are either in this group or in that group to make this true. So we want the union of these two sets, or we want to use the word or here. Either x is less than negative 4 to make this true, or x is greater than 4 to make that true. Okay, the word or here, the word and in the other problem. Now, here's what I want you to notice about this. We're not going to have the luxury of dealing with an interpretation graphically to begin with when the problems get a little more complicated. We're going to go directly to an algebraic form. And the algebraic form is from here we go to these two situations, these two cases, when we have an absolute value inequality. Now, notice the nature of these two. We have on one of them, we just drop the absolute value symbol and bring down. On the other one, we drop the absolute value symbol and we change the sense of the inequality and apply a minus sign here. You see, now we can there is a way for us to make a graphical interpretation. I think, though, that the speedy way to do this is to just go to these two, split into these two forms. Now, notice up here, the situation is a little bit easier when we have a less than situation. We use negative 4 on one end of this compound inequality and 4 on the other end, and just pop the value in the absolute value in between, and away we go. Okay, now I'm showing you this because now we want to jump into situations which are more complicated. How do we deal with these two? Well, the easy way to deal with this one, remember the less than, it's less than or equal to, but the less than idea puts whatever number here within a certain interval. We can say that the distance from 0 on the number line of whatever number that is less than or equal to 2. Well, how do we deal with that algebraically? Well, we just say that we go negative 2 is less than or equal to the number within absolute value, and that is less than or equal to 2. You see, and now we have a compound inequality which we can solve rather easily. Adding 3 in all parts, add 3 here, we get 1. Add 3 here, we get x. Add 3 here, we get 5. So x is between 1 and 5, including the endpoints, to make this true. Okay, now what about this situation? Well, it's the greater than situation. I think we need to split into the two cases. And by the way, let me show a way to split this into two cases as well, because some students find it easier to just say, well, in all absolute value inequalities, we can split into two cases. And here's how we would do that in this problem. We reason that in one case, we just drop the absolute value symbol. So we would write x minus 3 is less than or equal to 2. In the other case, we drop the absolute value symbol, we change the sense of the inequality, and we tack on a minus sign on the right side. So it would be x minus 3 greater than or equal to negative 2. And then we solve the two inequalities. And one little sidelight to this is that we have to put the word and or here. Now, we can make that decision right now, or we can make it a little bit later. If we want to make the decision now, we look at the inequality. This says less than. And my students say, well, gee, all you have to do is read this in a funny way, and you know what word to put here. Less than, and, so we put and here. Now, So we want the values that are in this set and in that set at the same time. That means we want the intersection of two sets. Now there's another way to make that decision, and I'll show it to you in just a moment. But this idea of reading this in a funny way is rather interesting. Less than, and then in the other direction, greater or, you see. So that's the way you make that determination. Well, in each of these, it's pretty easy to solve the inequalities. Here we would add 3 on both sides, and we would find x to be less than or equal to 5. And here we would add 3 on both sides. We would find x to be greater than or equal to 1. Now, the inequality that we had over there was the inequality 1 is less than or equal to x, and x is less than or equal to 5. And this means the same thing as these two inequalities separately if we put the word and in here, or we could say that it's the intersection of these two sets. Now, let's talk about why intersection works out so well. You know, if we're thinking about these two inequalities separately, x is less than or equal to 5. If 5 is here and 1 is here, then x is less than 5, less than or equal to 5, starts here and goes this way. X is greater than or equal to 1, starts here and goes this way. You see, so it's the intersection of those two that we're after, and that's why the intersection idea works here. Okay, and looking at the compound inequality, 1 is less than or equal to x is less than or equal to 5, or x is between 1 and 5. Gee, we're talking about the x values that are in here, so we're talking about the same set. Okay, that gives consistency to those two ideas, and therefore we can break into two cases in all problems involving absolute value inequalities. And here we would naturally do that. When greater than is involved, we naturally split into two cases. The two cases are these. X plus 1 is greater than 4. We just drop the absolute value symbol. And the other case is where we drop the absolute value symbol, change the sense of the inequality, and tack on a minus sign. So we would do that here by writing x plus 1 is less than negative 4. And now we solve these two. And it's important that we put the right word here. Now, in situations like this, where we have a distance from 0 on the number line that is greater than a certain value, then generally we're talking about an interval which lies out here and an interval which lies out here, and what we want is the union of those two sets. We want all the values that are either over here or over here. That makes this true, and that's why the word or is used here. But my students would say that this says greater than. Great or is the word used. Okay, subtracting 1 on both sides here, we find x to be greater than 3. And subtracting 1 over here, we find x to be less than negative 5. So graphically, we're talking about, let's see, x is greater than 3, x is less than negative 5. Greater than 3 means the value's out here. Less than 5, value's out here. So values that lie in either this interval or that interval would cause this absolute value inequality to be true. And we can either use this as our description, we can use this as our description. The word or corresponds with the idea of union. We could even use interval notation if we want to. If we're talking about this interval, it's the interval from negative infinity to negative 5. We're not including the negative 5 here, so we would write this. And then this interval is described in interval notation as 3 to infinity, and not including the 3, and we never include the infinity, and it's the union of these two sets that we're interested in. The American Kennel Club has developed guidelines for judging the features of various breeds of dogs. For collies, the guidelines specify that the weights for males satisfy the inequality given, where W is measured in pounds. Determine the interval on the real line in which these weights lie. Now, all we're doing is solving the inequality for W. And to do that, we change into the compound inequality form. Now, notice it's less than or equal to 1, so it's negative 1, and then this expression in the middle without the absolute value, and then 1 on the other side. To clear the fraction, we multiply in all parts by 7.5. 7.5 multiplied here gives us this. 7.5 times the fraction gives us a cancellation as expected, so we just bring down the numerator. 7.5 times 1 is 7.5. Now, adding 57.5 in all parts, we find that W is between 50 and 65. Now, these are weights for collies, so it's the weight needs to fall in the interval from 50 to 65 pounds, including those endpoints.